We have studied some vector operations. For example, we have studied vector addition, and when we added two vectors together, we got another vector. We multiplied a vector by a scalar, and when you do that, we also would get a result that is a vector. But now we're going to talk about this operation. We're going to talk about what's called the dot product. And you can see here how to take the dot product given two vectors. If we have a vector u and a vector v, notice we multiply the x components together, we multiply the y components together, or the horizontal components and the vertical components together, and then we take their sum. And notice the result is a scalar, a plain old number. So let's practice calculating dot products, and then we'll use it for something. So let's find u dot v given these vectors. So u dot v would equal, just using this formula, the product of the x components, 2 times 5 plus, now we multiply these components together, 1 times -6, and we have 10 minus 6, or 4. Now I want you to see v dot u. I want you to see whether the dot product is commutative. So we'll start with 5 times 2 plus -6 times 1. And of course, you can see that it gives us the same result. So in fact, the dot product is commutative. So let's jot that down as one of the important properties of the dot product. And that is that if you have vectors u and v, u dot v equals v dot u. There's another vector, or another property that I want to talk about just briefly, and that is when you multiply a vector by the zero vector, a vector v, the result is just the scalar 0, or the number 0. And let me show you why that's the case. If we took a vector v, we'll make it be this one. We're going to find the 0 vector dot v, and maybe you're not sure of what the 0 vector is. Let me write it right here. The 0 vector is 0, 0, right? And before I forget, I noticed I didn't put the arrow over the v. Let's pop that in. So if you dot 0, 0 with any vector, you'll notice that we get that 0 as a result. It's going to be 0 times 5 plus 0 times -6, and no surprise, the result is just 0. And I already wrote that on our list of properties. Let's go on. Let's practice with another pair of vectors. Notice in the previous problem I had our notation this way with the components written in the chevrons. This time the components are written with the unit vectors I and j, but the process is no different. Remember, it's just a different notation for representing the vectors. So let's just practice one more time. We're going to find u dot v by multiplying the x components, -1 times 10, and add that to 6 times -3. So we have -10 minus 18, or the dot product is -28. Let's do this problem, u dot u. So we're using the dot product with this vector. So u dot u would equal -1 times -1 plus 6 times 6. So we'll have 1 plus 36, or 37. And now let's look at this problem right here. The magnitude of u. The magnitude of u is equal to, remember, the square root of the x component squared, -1 squared, plus 6 squared, which is the square root of 1 plus 36, which is equal to the square root of 37. And compare these. Look at the radicand here. Do you see that the radicand, that's the stuff underneath the radical sign, is equal to our dot product? So when you square the magnitude, you'll get the dot product. So let's write that down as another important property here. The dot product is equal to the square of the magnitude. And while we're listing properties, I'm going to not prove this one to you, but I will tell you, and I'm thinking you won't be too surprised. If you have a vector u that you dot with v plus w, in fact, we have u dot v plus u dot w. So in fact, we can distribute with the dot product. So those are some important properties with respect to the dot product. Now let's move on. One way in which we use the dot product is to find the angle between two vectors. Now I have these two vectors, u and v, and I put their initial points together. And so the goal often is to figure out what would this angle be. So what I want to talk about is how we get the formula for finding that angle. And that formula is going to involve the dot product. In order to do that, I need to draw another vector right here. I'm going to make it start here, and maybe I'll do it in a different color. Start here and go this direction. And you'll notice if we turn this vector around, this is the vector v, this is the vector u. If I turn the vector around, I would have a -v plus u. Would be this resultant vector. Again, v goes this direction, so -v would go this direction. -v plus u, or another way of saying that is that it's u minus v. So now I have a triangle drawn, and we're going to try to find the measure of this angle. We know we could find the magnitudes of these three sides, and we want to find this angle. Well, we know a relationship between three sides and an angle, and it's called the law of cosines. So we're going to develop the formula using the law of cosines. Remember, that means we would take the square of this side. So we're talking about the magnitude of this side. So we have u minus v squared equals the sum of the squares of the other two sides. Now that means we have the magnitudes, those sides, their length is the magnitude, so we have the sum of the squares of those two lengths minus twice the product of the lengths of these two sides. So that's the product of the magnitude of u times the magnitude of v times the cosine of the angle in between. So again, that's from our law of cosines. Okay, now let's keep going. Let me remind you about this. Let me bring the properties back. Here it is. Remember, v dot v is the magnitude squared, or the magnitude squared gives you that dot product. We're going to use this property in the equation that we're working with. So we have the magnitude squared, and we're going to use our dot product. So that means here we have u minus v dot u minus v equals, now we have u dot, oh, that's a minus there, u dot u for this magnitude squared plus, here's another magnitude squared, v dot v minus, and let's leave this alone, 2 times the magnitude of u times the magnitude of v times the cosine of theta. Let me remind you what we're trying to find. We're trying to find a formula that will allow us to find theta easily if we know two vectors. So now let's keep going. I want to talk about this dot product right here. I want to figure out what this is. And I've already written it out for you. So let's look at this, because this is what we need. We need u minus v dot u minus v. Notice that's what this is. And it's really we'll use the distributive property twice. We saw that the dot product was distributive, right? So we distribute once, and then we distribute a second time. So we have expanded it to look like this, 4 dot products. But notice we have u dot v and v dot u. We know that's commutative, so it's u dot v and another u dot v, and that makes 2 of them. So looks very similar to what we get when we square a binomial. So here's the result. U minus v dot u minus v is this. Let's make that substitution. So we'll substitute that right. Let's do it this way so you can see it. We're going to make the substitution right here. So it is u dot u minus 2u dot v plus v dot v equals u dot u plus v dot v minus 2 times the magnitude of u times the magnitude of v times the cosine of theta. Whew, that's going to get a lot better in just a moment. Here's what I want you to notice. Right here we have u dot u on the left and we have u dot u on the right. Let's subtract that from both sides. Similarly, we have v dot v and v dot v. Let's subtract that from both sides. So now our equation is, on the left-hand side, negative 2u dot v equals negative 2 times the magnitude of u times the magnitude of v. That doesn't look very good, but that's a magnitude, times the cosine of theta. And let's divide. We'll divide by 2 magnitude of u times the magnitude of v. On this side, negative. And we'll divide by -2 times the magnitude of u times the magnitude of v. And we're to the end right here. Here's our big grand conclusion. We have the cosine of theta, because all of this cancels. Cosine of theta equals, and on the left-hand side, notice those -2's cancel. We have u dot v over the magnitude of u times the magnitude of v. And we have a formula for finding the angle theta that is between two vectors. So here's our formula. The cosine of theta equals the dot product of u and v in the numerator divided by the product of their magnitudes in the denominator. Let's use that idea to find the angle between two vectors. Here's the problem. We'll let u equal 4i minus 3j, and v will be 2i plus 5j. So let's write the formula, just so we get it down. It's the cosine of theta equals, remember the dot product of two vectors in the numerator, and in the denominator, it's the product of their magnitudes. So let's do it for this problem. We have the cosine of theta equals 4 times 2 plus -3 times 5 divided by, now we have some magnitudes to find, the square root of 4 squared plus -3 squared times the square root of 2 squared plus 5 squared. Let's do some simplifying. We have the cosine of theta equals, here we have 8 minus 15, that's -7, over, let's see, we have 16 plus 9, that's 25. The square root of 25 is 5. And we have 4 plus 25, that's 29. So we have the square root of 29. And now we can grab our calculator and find the angle between those two vectors. So we'll punch in inverse cosine of that ratio. So inverse cosine of -7 divided by 5 times the square root of 29. Oops, I punched it in funny. And I get about 105 degrees, or 105.1 degrees, depending on how many places you'd like to go. So if we were to draw these two vectors, and let's do that right here. We have this vector that is 4i minus 3j, looks like this, where this is 4 and this was -3. But here's the vector u, and the vector v is 2i plus 5j, so 2 and 5 up here, right? Where this is 2 and this is 5. And we have just found that this angle theta is about 105.1 degrees. I didn't label those components because the picture was getting a little bit busy, but it seems pretty close here. It seems a little bit obtuse there. Let's do another one. Let's find the angle between these two vectors. And again, I'm just having us practice the different notation. It doesn't matter how your vectors are given to you. The process is the same. So here we go. The cosine of theta, let's just write down the formula again so we get it down. u dot v over the product of their magnitudes. So we have cosine of theta equals 6 times 1 plus negative 2 times, you know, I did not want this problem to be this way. I'm going to change the problem right here on you because I was going to make another point. So I'm changing the problem. I copied it, I wrote it down wrong. This was supposed to be a positive 3 right here. So I'm changing the problem. So the vectors are 6, negative 2, and 1, 3. 1, positive 3. So if you're jotting this down as we move along, make sure you change that vector. So now back to our dot product. It was 6 times 1 plus negative 2 times a positive 3 over the product of the magnitudes. So we have the square root of 6 squared plus negative 2 squared. And we have the square root of 1 squared plus 3 squared. So I have the cosine of theta equals 6 plus negative 6, that's 0, over the square root of 40 times the square root of 10. Now I would simplify that denominator, but actually we know that doesn't matter what the denominator is because the numerator is 0. As long as the denominator is also not 0, we know we're solving this equation. The cosine of theta equals 0. We don't even need our calculator for this one. This is one that you should know. So we know that that means that theta equals 90 degrees. So if we put these two vectors together, and we have 6, negative 2, about like that. And we have 1, 3, about like that. We know if we put those initial points together, they would form a right angle. We say that two vectors that form a right angle when you put them together are called orthogonal. So it's a lot like being perpendicular, but it's the vocabulary that we use. They're orthogonal. If you were to move them together, they would form a right angle. And notice how we got there. We got that 90 degrees because the cosine of theta was equal to 0. So that brings me to this. If the angle, let's summarize here, if the angle between two vectors is 90 degrees, they're called orthogonal. It's a very common vocabulary. And two vectors u and v are orthogonal if and only if the dot product is 0. Let's come back here. Remember the cosine equaled 0? How did the cosine theta equal 0? It's because the numerator is equal to 0. And the numerator is the dot product. So your vectors are orthogonal if and only if the dot product is 0. So you'll have some questions that were asked, are the vectors orthogonal? The only thing then we need to determine is their dot product 0? So let's calculate it. U dot v for these two vectors. We have 6 times negative 6 plus negative 5 times 5. That's negative 36 minus 25. We can see it's not 0, but let's actually get a value. We see that it's negative 61. So are they orthogonal? The answer is no, they're not, because the dot product would need to be 0. So they're not orthogonal. Let's do another one. Let's find u dot v for these two. So we have u dot v for the vector 8, 5 and negative 10, 16. So we have 8 times negative 10 plus 5 times 16. And we have negative 80 plus 80 equals 0. And so we know, even without drawing the picture, that if we were to put those vectors together, they would form a 90-degree angle. So we'd say they are orthogonal. Now let's do this last problem. In this very last problem, we're going to dot u with the vector that is our 0 vector. Right? So when we do that calculation, we have u dot v equals 19 times 0 plus negative 11 times 0. And that is, of course, 0 plus 0. And we get 0. Well, remember, the idea was two vectors are orthogonal if and only if their dot product is 0. Notice when we did the dot product with this 0 vector, I called it the vector v. I could have just called it this, our 0 vector. That's what it is. We get 0. So it turns out, even though we have this vector that doesn't have a direction, we consider it to be orthogonal to 19, negative 11, and in fact we consider it mathematically orthogonal to any vector, which is kind of entertaining. So I hope you will go practice working some problems that use the dot product.